Bismillahirrahmanirrahim. We continue our discussion on number system. This is our last discussion on number system, and in this discussion we will be performing hexadecimal to octal conversion. This is the last conversion for hexadecimal number system. So far we have completed 11 number system conversions that include 3 conversions for the decimal number system, such as decimal to binary conversion, decimal to octal conversion, and decimal to hexadecimal number system conversion, a collective of 3 conversions for decimal number system. Then we have done 3 conversions for binary number system that include binary to decimal conversion, binary to octal number system conversion, and binary to hexadecimal number system conversion, a collective of 3 conversions for binary number system. Then we have also completed 3 conversions for octal number system that include octal to decimal conversion, octal to binary number system conversion, and octal to hexadecimal number system conversion, a collective of 3 conversions for octal number system. And then in previous lectures we performed 2 conversions for hexadecimal number system that include hexadecimal to decimal conversion, hexadecimal to binary conversion. So this collectively make a total of 11 conversions that we have completed so far. The last conversion for hexadecimal number which is left, and we are going to discuss it today, is hexadecimal to octal number system conversion. As you know, we have total of 4 number systems, and every number system is converted into 3 other number systems. So a collective of 4 into 3, 12 conversions can be possible. So this is our last and 12th conversion, number system conversion, that we are going to perform in today's discussion. As I just said, we are working on number system conversions. We have discussed all those agenda items in previous lectures, and we are currently working on conversions. As I just said, we have completed 11 number system conversions, and only the last one, the 12th conversion, is left, which is hexadecimal to octal number system conversion. We will be discussing technique how we can convert a hexadecimal number to octal number system. Let's start the discussion and see what are the methods that can be used to convert a hexadecimal number into its respective octal number system. Hexadecimal number, as you all know, consists of total 16 symbols, 10 digits from 0 to 9, and 6 alphabets from A to F. In such a way, A represents digit 10, B represents 11, C represents 12, D represents 13, E represents 14, and F represents digit 15. So hexadecimal number consists of total 16 symbols. Why we call them symbols? Because it does not only contain digits, it also contains alphabets as well. Hexadecimal numbers is used to represent the memory addresses in the latest digital computers. On the other hand, octal number system consists of total 8 numbers from 0 to 7. Octal number system is also used to represent memory addresses, but this was the older representation in earlier computer such as mainframe. So memory representation has now been replaced by using hexadecimal numbers. So today's discussion is we need to convert hexadecimal number to octal number. So what is the technique? We have two methods to perform this type of conversion. Both are indirect methods. There is no technique by which we can convert directly a hexadecimal number to octal conversion. First indirect method says that first we have to convert the given hexadecimal number to binary number, and then in next step the binary number is then converted to octal number. So how we can convert? We have already performed hexadecimal to binary conversion in previous lecture. So how we can convert hexadecimal number to a binary number? That we have to split every number in the given hexadecimal number in group of 4 binary digits. So in this way our hexadecimal number will be converted to binary number. And then what we have to do, we have to combine all the binary digits that are generated and start grouping them from right to left in groups of 3. As you all know, hexadecimal number is equal to 4 binary digits, while octal numbers are equal to 3 binary digits. So once you are going from hexadecimal to binary, you have to convert every given number in the hexadecimal number in group of 4 binary digits. And when we are going to octal number, so then the binary numbers are grouped in 3 groups, in group of 3 binary digits. You can consult the relationship chart that I had mentioned in the first lecture of this number system chapter, where I have represented the relationship between all the 4 number systems. So once we have converted a hexadecimal number in binary number, we will get 4 binary digits, and then we have to group those binary digits in group of 3, and this grouping will be started from right to left. And then every group of 3 binary digit, every digit within this group is multiplied by 2. The power of 2 will start from 0, and the multiplication process will move from right to left. After multiplication, we need to add the products, and the result will be an octal number for every given group. You are not supposed to add or multiply 2 individual groups. So this is how we can move from hexadecimal to octal. This is an indirect conversion. First we have to convert a hexadecimal number to binary number, and then from binary to octal conversion is performed. Let's see with few examples how we can perform or how we can apply this first method. Let's see, we are given a hexadecimal number 1BC, and we have to convert it to octal number system. Here we are going to use the indirect method I just explained, the first indirect method. We will be going for the second indirect method later on. So first indirect method says we have to first convert this hexadecimal number to binary number. And the method is we have to split every number in this given hexadecimal number in group of 4 binary digits. So how we can do it? This is the given number 1BC. Every number is splitted. So you have to write every number separately. As you know, here B shows number 11 and C shows number 12. So every individual number is now grouped or split in group of 4 binary digits like this. 4 binary digits in which the bases are 2 and the powers starts from 0. So 4 binary digits for every number is formed. So for our understanding, we further split this group. 2 raised to power 3 is equal to 8. 2 raised to power 2 is equal to 4. 2 raised to power 1 is equal to 2, and 2 raised to power 0 is 1. So this is for our understanding. You can skip this step if you can, without this step, solve the conversion. Now we have to generate 1 by adding the given 4 binary digits. So we have to see which numbers are going to generate 1. So those numbers will be kept on as 1, while rest of the bits will be kept as off in shape of 0. So here you can see only the first bit is enough to generate 1. So first bit is set as 1, while rest of the bits will be set to 0. So this will ultimately generate, this sequence 4 bits will generate hexadecimal 1. Next number is 11. So we have to see which numbers are, if added together, can generate 11. So those numbers will be switched on and rest of them will be switched off. So if you can see, 8 plus 2 plus 1 will generate 11. So that means if we switch on first, second and fourth bit and switched off the third bit, so it would generate number 11. So group of 4 is created, which is generating the given hexadecimal B. Next number is 12. So which numbers are added together, which bits are added together in order to generate C, which is 12. So those bits will be set on and rest will be kept as 0. So you can see if we add 8 with 4, this will generate 12. That means bit number 3 and 4 are set as 1, while first 2 are kept as 0 in order to generate 12. Here you can see this is how we have performed the conversions. So now octal hexadecimal to binary conversion is completed. Now is the time to move to octal conversion. We have generated binary numbers and now we have to move to octal numbers. How octal number can be generated? We are now supposed to group these binary digits in group of 3, and this grouping will start from right to left as the method says. So starting from the very right, we are going to group these binary numbers in group of 3. So first group is 0, 0, 1, second group is 1, 1, 1, third group is 0, 1, 1, and fourth and last group is 0, 0, 0. So in this way we have generated 4 groups. Let me write it here. So 4 groups are formed. Now in next step we have to multiply every digit within every group with 2. The power of 2 will start from 0 and the multiplication will move from right to left like this. So let's see, the first group is 1 0 0. 0 is multiplied by 2, the power of 2 is 0. Second 0 is multiplied by 2, the power of 2 is 1. And 1 is multiplied by 2, the power of 2 is 2. Second group is 1 1 1. So 1 is multiplied by 2, the power of 2 is 0. 1 is multiplied by 2, the power of 2 is 1. And last one is also multiplied by 2, the power of 2 is 2. You can see here the multiplication process is moving from right to left for every group. Here you can see. And the individual multiplications are getting added together within the group. You are not supposed to add two different groups. Here you can see every multiplication or every product is getting added inside the group. Similarly, the third group is 1 1 0. So 0 is multiplied by 2, the power of 2 is 0. 1 is multiplied by 2, the power of 2 is 1. And last one is multiplied by 2, the power of 2 is 2. The individual products are getting added together. Last group consists of 3 zeros. So all the 3 zeros are being multiplied with 2. The power of 2 starts from 0 till 2 and it will ultimately generate 0. So after clearing up the powers, this is the answer. Here you can see anything which is multiplied by 0 is ultimately resulting is 0. So the first group, first 0 is generated, second 0 is generated, and for the third bit 2 raised to power 2 is 4 and 4 is being then multiplied by 1 while the products are added together. For second group 2 raised to power 0 is 1 and 1 is being multiplied by 1. 2 raised to power 1 is 2 and 2 is multiplied by 1 and 2 raised to power 2 is 4, 4 is multiplied by 1. For third group, anything multiplied by 0 is ultimately 0. 2 raised to power 1 is equal to 1. 2 raised to power 1 is equal to 2. It is multiplied by 1. 2 raised to power 2 is 4. It is multiplied by 1. And in the last group, you can see we are getting 3 zeros. So after multiplication, this is the answer. You can see first group is generating 4, second group is generating 4 plus 2 plus 1, third group is generating 4 plus 2 plus 0, and last group is generating 0. After adding the products, this is the result. First group is generating number 4, second group is generating 7, third group is generating 6, and last group is generating 0. So how you can write the answer? Collectively, 1 BC, which was a hexadecimal number, has been converted to 6748 in base 8. You can see 0 towards the left, this one, 0 towards the left A of 6 is not required to be written as it is not going to change the result. This is the least significant 0. But if there had been any 0 towards the right hand side, so you would have written it as these zeros are the most significant. That is why I have skipped this first 0 and the answer is just 674 in base 8. If you write this 0, again it's up to you, but we don't write it as it doesn't bring any change on the final answer. So this is how we convert hexadecimal number to octal number using first indirect method. Here we first converted hexadecimal number to binary number and then the binary numbers are converted to octal number. Both the methods, hexadecimal to binary and binary to octal, have already been discussed separately in previous lectures. Now let's see another method to convert hexadecimal number to octal number. This is second indirect method. In this method, First we have to convert the given hexadecimal number to decimal number, and then this decimal number will be then converted to octal number. So this is again an indirect method in which we have to first convert the given hexadecimal number to decimal number, and when we have got the decimal number, so this decimal number will then be converted to octal number. Let's see how we can perform this type of conversion using this second indirect method with few examples. But keep in mind, we have already performed this type of conversion earlier. For example, we have done hexadecimal to decimal conversion in previous lectures, and also we have done decimal to octal conversion in previous lectures. So you must be aware of both the methods. Now let's apply this indirect method on an example. Here we are given a hexadecimal number C1 and we have to convert it to octal number using second indirect method. Second indirect method says first we have to convert the given hexadecimal number to decimal number. And what is the procedure? This is the given hexadecimal number C1 and we have to convert it into decimal number first. As you know, C represents number 12. So what is the technique to convert hexadecimal number to decimal number? Here it is. We have to multiply every given number within the hexadecimal number with 16. The power of 16 starts from 0 and multiplication process moves from right to left. So first number is 1. 1 is being multiplied by 16. The power of 16 is 0. Second number is C. C is being multiplied by 16. The power of 16 is 1. Multiplication is moving from right to left, and all the individual numbers are getting, individual products are getting added together. So after clearing up the powers, 16 raised to power 0 is equal to 1. 1 is multiplied by 1 and 16 raised to power 1 is equal to 16. 16 is multiplied by 12 as C represents number 12. After multiplication, this is the answer, and when we add up the products, the result is 193. This 193 is a decimal number. So don't stop here. This is not the octal number. As you can see, every digit is not within the range of octal number system, as 9 is the number which is not within the range of octal number system. So we have to convert it into octal number. How will you write this answer? C1 in base 16 is equal to 193 in base 10. So we have converted one step. We have done hexadecimal to decimal conversion. Now we have to move from decimal to octal conversion. And what is the technique? The given number, the given decimal number that we just generated is 193. Here you can see we have generated this number just now. Now 193, which is a decimal number, is to be converted to octal number. And what is the procedure? You need to divide this decimal number repeatedly by 8 until the quotient and remainder comes within the range of octal number system. So let's do it. 193 is being divided by 8 repeatedly. The answer, the quotient is 24 and remainder is 1. Now 24 is again divided by 8 and the quotient is 3 and remainder is 0. So here you can see the quotient is within the range of octal number system. So it cannot be further divided by 8. So we stop our divisioning here. How we write the answer? In bottom up manner. So this is the collective answer. 193, which was a decimal number, has been converted to an octal number, which is 301. You need to first write the bottom numbers. 30 are the bottom numbers and 1 is the top number. So 301 in base 8 is the conversion for 193 in base 8. So how you collectively write the answer? C1, which was a given hexadecimal number, has now ultimately been converted to 301, which is an octal number. So here we have used again an indirect method to convert a hexadecimal number to octal number. And what was the technique? First we converted the given hexadecimal number to decimal number, and then the decimal number is converted to octal number. Now let's see if we are given hexadecimal fractions. So how we can convert them to octal number having fractions? So the method remains the same. Both the indirect techniques can be used. So I'm going to use the first indirect method, that we have to first convert the given hexadecimal number to binary number, and then from binary to octal conversions will be performed. You can use the second technique as well, in which you have to first convert the given hexadecimal number to decimal number, and then from decimal to octal conversion can be performed. Let's see for fractions how we can apply this first indirect method. Here we are given a hexadecimal fraction 0.76c, and we have to convert it into octal number using first indirect method. The indirect method says we have to convert this number first to binary number. So how we can convert it into binary number? Every individual number within the given hexadecimal number is split in group of 4 binary digits. So split the number in this way, write them separately. See here, you can see C is equal to number 12. So we have written every number individually, and you can see here the point, the decimal point stays at its place. Do not change the position of the decimal point. Now you have to split these every individual number in group of 4 binary digits like this. 4 binary digits are formed, so for our understanding we write it further for clarification. For example, 2 raised to power 3 is 8, 2 raised to power 2 is 4, 2 raised to power 1 is 2, and 2 raised to power 0 is 1. We write this step only so that we can better know which bits can be added together in order to generate the respective hexadecimal number. If you can do it directly, you can skip this step. Skip this step only in red. You are not supposed to skip the first step. The decimal point stays at its place. So now we have to see which numbers are added together to generate 0. But here you can see all the bits must be 0 in order to generate 0. So we keep all the 4 bits as 0. The point stays at its place. Next number is 7. So which bits are added together to generate 7? So here you can see 4 plus 2 plus 1 is equal to 7. That means first 3 bits are set to 1 and last bit is set to 0 in order to generate 7. Next number is 6. So which bits are added together to generate 6? So here you can see 4 is added to 2 to generate 6. That means second and third bit is set to 1 while first and fourth bit is set to 0 in order to generate 6. Similarly, last number is C, which is 12. So which numbers or which bits are added together to generate 12? So that is 8a plus 4 is equal to 12. That means if we switch off first 2 bits and switch on the last 2 bits, so this will generate number 12. So this is our conversion from hexadecimal to binary. Now in next step we have to group these generated binary numbers in group of 3 bits. And the grouping must start from right to left for the integer part and from left to right for the fractional part. So you can see this is the decimal point. Decimal point stays at its place. So this is the integer part. This one is the integer part, while this one towards the right of the decimal point is the fractional part, while towards the left of the decimal point is the integer part. So integer part, the grouping starts from right to left, or you can simply say start the grouping for both the parts right from the decimal point. So for the integer part, the grouping moves from right to left. This is first group, 3 zeros, and last 0 is left alone. So we can add 2 extra zeros in order to complete this group. But since 0 will not change the result, so 1 0 is enough. But you can add 2 extra zeros to complete its group. But since it is again going to generate 0. Now for the fractional part, again we are going to group the digits starting from the decimal point. So this is the decimal point. We are going to group it from here. First group is 0 1 1. Start the grouping from left to right. Second group is 1 0 1. Third group is 1 0 1. Fourth group is 1 0 0. So we are getting 4 groups towards the right hand side or for the fractional part, and 1 group or 2 groups of zeros on the integer side or left hand side. So this is how we write the groups. Now every digit within every individual group is multiplied by 2. The power of 2 is started from 0 and the multiplication process moves from right to left. So this is how we do it. First group is 1 0 0. 0 is multiplied by 2, the power of 2 is 0. Next 0 is multiplied by 2, the power of 2 is 1, and 1 is multiplied by 2, the power of 2 is 2. Next group is 1 0 1, so 1 is multiplied by 2, the power of 2 is 0. 0 is multiplied by 2, the power of 2 is 1, and 1 is multiplied by 2, the power of 2 is 2. Third group is again 1 0 1, so 1 is multiplied by 2, the power of 2 is 0. 0 is multiplied by 2, the power of 2 is 1, and 1 is multiplied by 2, the power of 2 is 2. Fourth group is 0 1 1, so 1 is multiplied by 2 and the power of 2 is 0. 1 is multiplied by 2, the power of 2 is 1, and 0 is multiplied by 2, the power of 2 is 2. Decimal point stays at its place. Towards the left hand side are 3 zeros which are getting multiplied by 0. The power of 2 starts from 0 to 2, but ultimately this would generate 0. You can do the same procedure for the next group of zeros as well, but again this is not required as it would ultimately generate another 0. So after clearing up the powers, these are the answers. Anything multiplied by 0 is ultimately resulting in 0, so 2 zeros for the first group, and then 2 raised to power 2 is 4, 4 is being multiplied by 1, the result is 4. For the next group, 2 raised to power 0 is 1, 1 is multiplied by 1, the result is 1, and anything multiplied by 0 is 0. 2 raised to power 2 is 4, 4 is multiplied by 1, the result is 1. For the third group, 2 raised to power 0 is 1, 1 is multiplied by 1, the result is 1. Anything multiplied with 0 is 0, 2 raised to power 2 is 4, 4 is being multiplied by 1, the result is 4. 2 raised to power 2 is 4, so 4 is multiplied by 1, the result is 4. Here again 2 raised to power 0 is 1, 1 is being multiplied by 1, the result is 1. 2 raised to power 1 is 2, 2 is multiplied by 1, so result is 2, and here for the last bit, anything multiplied by 0 is ultimately 0. Point is at its place here, you can see, and the last towards the left hand side, this group is generating all zeros. After adding up the products, the result is this. 0 point first group for the fractional part is generating 3, second group is generating 5, third group is generating 5, and last group is generating 4. So after grouping up all the answers, how we write the collective answer? 0.67C in base 16 is equal to 0.3554 in base 8. This is the answer for the fractional hexadecimal number. So how we converted it? First we converted the given hexadecimal fraction to binary fraction, and then from binary fraction to octal fraction. Let's see another example. Here we are given a hexadecimal fraction 0.ABEF, and we have to convert it to octal fraction. So how we can do it? First we have to convert it to binary fraction, and for this we have to consider every individual number in the given hexadecimal number as independent number, like this. Here you can see A represents 10, B represents 11, E represents 14, and F represents 15. So this every number is then split in group of 4 binary digits, like this. So for our understanding, we write 2 raised to power 3 as 8, 2 raised to power 2 as 4, 2 raised to power 1 as 2, and 2 raised to power 0 as 1. Decimal point stays at its place. Now we have to see which numbers can be added together to generate the given hexadecimal number. 0 is the first hexadecimal number, but no number can be added to generate 0. That means all the bits, all the 4 bits are to be kept as off. So 4 zeros are formed here. Then point at its place. Next number is 10. So which numbers are added together to generate 10? 8 is, if added with 2, it would generate 10. That means bit number 2 and 4 are set as 1, while 2 others are set as 0 to generate 10. Next number is 11. That means which bits are added together to generate 11. If 8 is added to 2 and 1, it will generate 11. That means first, second, and fourth bit is set to 1, while third bit is set to 0 in order to generate 11. Next number is 14. So which bits are added together to generate 14? So if we add 8 with 4 and 2, so it would generate 8 plus 4 plus 2 would generate 14. So second, third, and fourth bits are set to 1, and first bit is set to 0 in order to generate 14. While last number is 15. So which numbers are, or which bits are added together to generate 15? So if we add all the bits, 8 plus 4 plus 2 plus 1, so this would generate 15. That means all 4 bits are set to 1. So this is how we have performed the conversions. So we have completed hexadecimal to binary conversion. So now is the time to go from binary to octal conversion. And what is the procedure? We need to group these binary digits. So for the integer part, this is the integer part, the grouping moves from right to left, and this is the fractional part, and for the fractional part the grouping moves from left to right, or simply start the grouping right from this decimal point. So one grouping will move from left to right and other grouping will move from right to left. So towards the left hand side of this decimal point, first group is 0, 0, 0. This is the first group right from the decimal point, while second group is only left with 1 0. You can complete the group by adding 2 extra zeros, but we do not need it, as ultimately it would generate 0. So one group of zeros is enough. Then towards the right hand side of the decimal point, the grouping will move from left to right. So first group is 1 0 1, second group is 0 1 0, third group is 1 1 1, fourth group is 1 1 0, fifth group is 1 1 1, and sixth group is incomplete, having just one digit. So we can complete it by adding 2 extra zeros. So these are our groups. This is how we write them. Now we have to Multiply every digit within every group with 2. The power of 2 starts from 0. Multiplication process move from right to left. This is how we do it. Here you can see first group towards the fractional part is 1, 0, 0. 0 is multiplied by 2. The power of 2 is 0. 0 is multiplied by 2. The power of 2 is 1. 1 is being multiplied by 2. The power of 2 is 2. Next group is 1, 1, 1. 1 is multiplied by 2. The power of 2 is 0. 1 is multiplied by 2. The power of 2 is 1. And last one is multiplied by 2. The power of 2 is 2. Third group is 1, 1, 0. 0 is multiplied by 2. The power of 2 is 0. 1 is multiplied by 2. The power of 2 is 1. And 1 is multiplied by 2. The power of 2 is 2. Next group is 1, 1, 1. So 1 is multiplied by 2, the power of 2 is 0, 1 is multiplied by 2, the power of 2 is 1, and last one is multiplied by 2, the power of 2 is 2. Another group is 0, 1, 0. So 0 is multiplied by 2, the power of 2 is 0, 1 is multiplied by 2, the power of 2 is 1, 0 is multiplied by 2, the power of 2 is 2. The last group for the fractional part is 1, 0, 1. So 1 is multiplied by 2, the power of 2 is 0, 0 is multiplied by 2, the power of 2 is 1, and 1 is multiplied by 2, the power of 2 is 0. The decimal point is at its place, and towards the left hand side are all zeros which are getting multiplied by 2. The power of 2 goes from 0 to 2. So after clearing up the powers and multiplication, this is the result. So for anything multiplied by 0 is ultimately resulted in 0. So 2 zeros for the first group, and 2 raised to power 2 is 4, which is multiplied by 1. The result is 4. For the second group, 2 raised to power 0 is 1. 1 is multiplied by 1. The result is 1. 2 raised to power 1 is 2. 1 is multiplied by 2, and the result is 2. 2 raised to power 2 is 4. 4 is multiplied by 1. The result is 4. And similar multiplications are done for all the groups. After adding up the products, these are the results. First group generates number 4, second group generates number 7, third group generates number 6, another group generates number 7, another group generates number 2, and number 5 is generated by another group. So these are the groups, answers for the groups on the fractional side. The decimal point stays at its place, and towards the left hand side is a 0. So you can see here all the numbers, all the generated numbers are within the range of octal number system. How you collectively write the answer? This was a given hexadecimal number 0.ABEF, and we have converted into octal number, which is 0.527674. Every number here, you can see every number in this converted number is within the range of octal number system. So this is how you can perform hexadecimal fraction to octal fraction. You can use the second method, second indirect method as well to perform fractional conversions, in which you can use first hexadecimal to decimal conversion, and then from decimal to octal conversion. Now let's combine both the parts, the integer part and the fractional part. We are given a hexadecimal number D5.7. We have to convert it to octal number. So again, I am using the indirect method 1, in which we have to first convert the given hexadecimal number to binary number, and for that we have to treat every number separately. Like D is 13, then 5, point is at its place, and 7. And this every number is now split in group of 4 binary digits like this. For our simplicity, we have written the powers in simplified form, but the point goes at its place. The decimal point is at its place here, you can see. Now, we have to generate 13. So, which bits are added together to generate 13? If we add 8 with 4 and 1, so this would generate 13. That means if we switch on first, third and last bit, and keeping off the second bit, this will generate 13. Next number is 5. So how we can generate 5? If we add 4 with 1, this will generate 5. So that means 1, first bit and third bit is set to 1, while second and fourth bit is set to 0. Point is at its place, last number is 7. How we can generate 7? If you add 4 with 2 with 1, this would generate 7. That means first 3 bits are set to 1 and the 4th bit is set to 0. So these are the generated binary numbers. Now we have to move to octal number. We have converted the numbers in binary form. So now from binary to octal conversion. For that you have to group the given binary number. So starting from the decimal point, if we group the fractional part first, so this is the fractional part. So first group is starting right from the decimal point. This is the first group 0, 1, 1, and second group is left with just 1 digit. So we can complete the group by adding 2 zeros. So 2 groups are formed on the fractional side. While towards the integer side, here you can group by moving from the decimal point. So first group is towards the left hand side. The first group is 1, 0, 1, second group is 0, 1, 0, and last group is 2 ones. So in order to complete the group, we have to add 1 0 to it. So these are the groups like this. 3 groups towards the left side and 2 groups towards the right hand side. Now we have to multiply every digit within every group with 2. The power of 2 starts from 0 and the multiplication moves from right to left like this. So you can see first group towards you can see notice the position of the decimal point. We have not changed the location of the decimal point. So first group towards the fractional part are 1, 0, 0. 0 is multiplied by 2, the power of 2 is 0. 0 is multiplied by 2, the power of 2 is 1. And 1 is multiplied by 2, the power of 2 is 2. Second group is 0, 1, 1. 1 is multiplied by 2, the power of 2 is 0. 1 is multiplied by 2, the power of 2 is 1. And 0 is multiplied by 2, the power of 2 is 2. Towards the integer part, first group is 1, 0, 1. 1 is multiplied by 2, the power of 2 is 0. 0 is multiplied by 2, the power of 2 is 1. And 1 is multiplied by 2, the power of 2 is 2. Second group is 0, 1, 0. 0 is multiplied by 2, the power of 2 is 0. 1 is multiplied by 2, the power of 2 is 1. And 0 is multiplied by 2, the power of 2 is 2. Last group is 0, 1, 1. So 1 is multiplied by 2, the power of 2 is 0. 1 is multiplied by 2, the power of 2 is 2. And 0 is multiplied by 2, the power of 2 is 2. Position of decimal point stays the same. After clearing up the powers and multiplication, these are the answers. So here you can see anything multiplied by 0 is resulting in zeros. 2 zeros for the first group, and 2 raised to power 2 is 4. 4 is being multiplied by 1, the result is 4. For the second group, 2 raised to power 0 is 1. 1 is multiplied by 1, the result is 1. 2 raised to power 2 is 1. 1 is multiplied by 1 and the result is 2. 2 raised to power anything multiplied by 0 is ultimately resulting is 0. The individual products within the group are getting added together. Similarly, the location of decimal point is at its place and we perform the same multiplication for the left hand side. After adding up the products, and this is the answer. So you can see for the first group on the integer side it generates number 3, second group generates 2, third group generates 5. Decimal point is at its place towards the right hand side. First group generates 3 and second group generates 4. So after grouping up all the answers, the result can be written as D 5.7 in base 16 is equal to 3 to 5.34. So every number within this generated number is within the range of octal number system. So this is the first indirect method. You can use the second indirect method as well. Let's see another example. We are given a hexadecimal number 2.3. We have to convert it to octal number system using the first indirect method. So we have to write both the numbers separately with decimal point at its place and split both the numbers in group of 4 binary digits in this way. So now we have to generate 2. So which bits are added together in order to generate 2? If you see, if the second bit is just kept on and 3 of the bits are kept off, so this would generate number 2. Decimal point is at its place. Similarly, if you have to generate number 3, First two bits, 2 plus 1 is 3. So if you switch on the first two bits and switch off the last two bits, this will generate 3. So these are the generated numbers. Now we have to group them. We have converted hexadecimal to binary, and now we have to go from binary to octal. So we have to group these generated binary numbers. How you can generate? Towards the fractional part, start grouping from the decimal point. So one will go from left to right and other side will go from right to left. So fractional part is grouped from left to right. First group is 0, 0, 1 and last group is 1 alone. We can add 2 extra zeros to complete the group. Towards the left hand side, we are going to group from right to left. So first group is 0, 1, 0 and last group is 0 alone. You can have 2 extra zeros, but ultimately this would complete generate 0. So no need to go further for this. So these are the generated groups. Now we have to multiply every digit within every group with 2. The power of 2 starts from 0 and multiplication moves from right to left like this. So first group towards the fractional part is 1, 0, 0. 0 is being multiplied by 0. The power of 0 is being multiplied by 2. The power of 2 is 0. 0 is multiplied by 2. The power of 2 is 1. And 1 is being multiplied by 2. The power of 2 is 2. Second group is 0, 0, 1. So 1 is multiplied by 2. The power of 2 is 0. 0 is multiplied by 2. The power of 2 is 1. And 0 is multiplied by 2. The power of 2 is 2. Point is at its place. So towards the left hand side, the group is 0, 1, 0. 0 is multiplied by 2. The power of 2 is 0. 1 is multiplied by 2. The power of 2 is 1. 0 is multiplied by 2. The power of 2 is 2. Last group is all zeros which are multiplied by 2. The power of 2 starts from 0 to 2. This would ultimately generate 0. So after clearing up the products and multiplication, the first group is generating 4 plus 0 plus 0. Individual products within the group are added together. Second group is generating 0 plus 0 plus 1. Point is at its place. Towards the left hand side, the group is generating 0 plus 2 plus 0, and then second group is generating 0. After adding up the products, the results are, for the left hand side, the result is 0, 2. You can skip this 0 towards the left hand side. Point is at its place, and the two groups on the fractional sides are generating 1 and 4. So how we write the answer? 2.3 in base 16 is equal to 2.14 in base 8. So 0 here towards the left hand side of the decimal point can be skipped unless and until no further number is added towards the very left of the 0. While zeros on the right hand side of the decimal point are the most significant one, you cannot skip them even if they are towards the very right. No other number is with them. So you can write the answer as 2.14 in base 8. This is your assignment. You are supposed to convert the given hexadecimal numbers to octal numbers. You can use any of the two techniques I have just discussed to convert these numbers. The assignment will be uploaded on KCMS and you are supposed to upload it within due date. That is all with this chapter. We have completed the number system chapter, in which we have studied 4 different types of number systems, that are decimal number system, binary number system, octal number system, and hexadecimal number system. Decimal number system is a common number system that we commonly use in our daily routine. It is native to human language and it consists of total 10 digits, 0 to 9. It is represented with base 10, but since this is native to human language, generally base 10 is not written with decimal numbers. So if you find any number having no base written with it, so it is understood that number is a decimal number. Binary number system is a native computer language. It consists of 2 digits, 0 and 1. But don't forget to write base 2 with it. Why? Because 0 and 1 are also part of decimal number system, octal number system and hexadecimal number system. Third number system is octal number system that consists of total 7 digits, 0 to 7. And it is written with base 8. Fourth number system is hexadecimal number system. It consists of total 16 symbols that include 0 to 9, total 10 digits, and A to F, total 6 alphabets. Base 16 is written with the numbers converted or with the hexadecimal numbers. We then performed total 12 conversions. Every number system is converted to 3 other number systems. So we are having 4 number systems and they are converted to 3, and every one is converted to 3 other number systems. So a total of 4 into 3, 12 conversions have been performed. With this, number system chapter comes to an end. In the next lectures, we will be discussing new chapter with new topics. I hope this chapter is clearly understood to you. Still, if you have any queries, you can ask on KCMS or on my email. That's all for now. I thank you all.